hear me fine? I think so. So, my name is Damiano Melotti, and today I'm going to talk a bit about our work on the Titan M chip, a security chip in Google Pixel devices. So, this research was conducted mainly by me. I am a security researcher at Quarkslab, mostly working on low-level Android projects. But I would not be here without the contribution of Maxime, who is my tech lead and also in my team working in embedded software security. So big up for him. And we are about to dive into a component that was introduced fairly recently in Google Pixel devices, which is this Titan M chip. And in short, this is a chip that implements some critical security features for the security model of Pixel devices. It was present from Pixel 3 to 5. Now from Pixel 6, there's a new iteration. There is the Titan M2. We're going to talk about the Titan M today. The idea is that with a separate chip, you can have improved protection against harder level attacks, side channel, and so on. Which is a bit of the reason why it was introduced. So it is a chip based on Cortex M3, so ARM architecture, and it is running a closed source OS, but that is heavily inspired from EC, which is instead open source, and it is an operating system that can be seen in embedded controllers for Chromebooks mostly. The nice part of this firmware is that it is really simple. There is no dynamic allocation, and the memory layout is static. There are different tasks that can be seen a bit as independent execution, dependent programs that perform certain features. And then it communicates with the main OS through the SPI bus, while the UART is used only for debugging, and it doesn't get to the Android interface. This is not the first time we talk about this chip. In the last year, we gave a first public talk about it, where we kind of started researching and getting familiar with the chip that was this new and not so known to the community. And kind of to wrap up what we already did, we started from reverse engineering of the firmware. The firmware can be found on the Android file system. It's not encrypted or obfuscated. You can start reversing immediately. And we kind of got our hands dirty while doing some reverse engineering. We also developed some tools to interact with the chip at software and hardware level. And we ended up also soldering stuff on the actual board to perform hardware man-in-the-middle. This is something that was useful to intercept and communicate with the chip in all the phases of the functioning of a phone. But here, the shout-out goes to Phil Tuven, a colleague of mine who made some crazy stuff with the hardware work. We, of course, wanted to find some vulnerabilities, and in the end we did find a few of them. The most remarkable is the second one you see in this slide. It is a downgrade vulnerability that allowed us to flash any firmware of also older versions in the chip. And thanks to that, we could roll back to a vulnerable version and exploit a vulnerability that was already patched in the newest ones to write the first code execution exploit in the chip. So this is the old stuff that we did, and that was wrapped up in putting a link here to a talk we did. But today, I want to kind of give a further angle to this research project and show how we try to do vulnerability research on this kind of target. And when I say vulnerability research, what we mostly did was fuzzing, which is turns out to be pretty useful even in these situations. in different settings that we will discuss a little bit. And then I will dive into one vulnerability that we found that gave us the chance to obtain code execution again on the chip, this time, of course, using this 0-day. Before starting, let's have a look a bit on the attack surface that is available when trying to approach the Titan M. So in this slide, I try to summarize a bit how Android and the chip communicate. You have several HALs, hardware abstraction layers, that send protobuf encoded messages to the daemon, which is the one who talks to the driver and goes to the chip through the SPI bus. So when trying to approach the surface of this target, what one can try to do is try to bypass the daemon and talk directly with the driver. This is what we did with a binary that we called the NOS client. This was a custom client to talk directly with the driver, bypassing the whole system. And this was the base for the first type of research, vulnerability research that we did, which was black box fuzzing. So when I say black box, what I mean is the classical situation where you only have a channel to communicate with what you are trying to test, and then only a way to tell if something happened, without any further visibility over what's going on in the target. In our case, we have the channel that is given by NOS client, this binary we developed. We know the format of the messages thanks to the open source protobuf definitions, so we can use them to mutate with libprotobuf mutator. And then, based on a return code, that is the signal that tells us whether the chip is crashing or not. We start from an empty, from a corpus made of empty messages with some particular fields that were set thanks to some sniffing done with freedom. This is not rocket science. And on the return code that we check, in this slide you can find that defines the different return codes. And in particular, we are interested in any return codes that are bigger than 2. This is because 2 it means error internal. Turns out this is what happens when the chip crashes, but all the others are also sort of interesting. So we run this fuzzer on this setting, first on an old firmware that we knew had quite a few bugs, and we found most of them, including the one we exploited earlier, if you remember, to get code execution thanks to the rollback. We also repeated the research on the latest firmware at the time, but we only found 2, in fact, null pointer references that turn out to be in the same function, which were causing a crash on the chip, but were not considered serious enough to be considered vulnerabilities by Google when we reported them. But all this came after a few minutes of fuzzing, which kind of takes us to the main pros and cons of this approach. And of course, the pros go in the direction of finding bugs. So if we can find bugs, it means the approach is interesting, and at the end of the day, we did. So that's nice. And of course, when a bug is found in this approach, you immediately also have a proof of concept because of the practicality of black box fuzzing. It is also fairly easy to mount, but the main issue is that we are probably only scratching the surface. We are only hitting shallow states of the target, which means we are not really getting over some of the superficial checks, most likely, because we have no visibility over what is going on the target. That's the main drawback, and that's also the main reason why we wanted to try something different. And by something different, I mean emulation-based approaches. So once we know how the operating system works and how we can set it up, also leaking memory thanks to the read primitive that we built upon the code execution exploit on the old version of the firmware, what we can do is put all together and mount an emulator. So control the execution of the firmware by rehosting it in an emulator, and then use this as the starting point for a different fuzzing approach where we have visibility over what is going on. To emulate Titan M, we ended up choosing Unicorn. There are quite a few frameworks out there, but Unicorn was for sure the easiest to use. It is based on QEMU, but it only emulates the CPU, so you don't achieve full system emulation. You just give it a starting point and end point, and after setting up the memory, it will take care of emulating instruction by instruction. But the probably best part about using Unicorn is that it integrates really well with AFL++, which I'm sure most of you are already familiar with. It's one of the most famous fuzzers. And with its Unicorn mode, you can basically fuzz anything that can be emulated with Unicorn. All you need is a callback to place the input at the right address in memory. And AFL will detect crashes when Unicorn crashes. On top of that, we can also use custom mutators. This is a feature of AFL, which makes it even more interesting when it comes to fuzzing and leveraging some sort of grammar, which is this case. So we can again rely on libprotobuf mutator to embed, mutate using the grammar that we have. And we only need to, as I said, provide an entry point and an exit point for our fuzzer. And we focused mostly on two of the tasks, which are identity and key master. You don't need to know specifically what they do, but they are the larger ones that are present in the system, and where there's a little bit more of the bug-prone code. We also fuzzed another one that is called Weaver, but that was particularly small. So of course we try to cover the larger code portion. And as we did before, can we still find some bugs that we know are there before trying to find some new? And the answer is yes. We can find the same bugs we found with the black box approach, but we miss at least one, and that's what takes me to also the disadvantages of emulation-based approaches, because like we know, there is almost never a free lunch, and when trying to emulate code from hardware, from code that is so close to the hardware, it is really difficult to deal with hardware dependency and code that is impossible to be emulated. So we need a lot of hooks, which means essentially you know that that function will try to read some value that nobody will ever set, so we cannot execute it, we cannot emulate it. This means that the portion of code we cover also has some limitations, and we are also not entirely sure of being able to detect every single bug that we will be able to reach, because Unicorn is it doesn't present any particular instrumentation, and in-page overflows or off-by-ones are still tricky to detect. The final point is that is a bit of our choice. No, I said Unicorn doesn't offer full system emulation, and that's what we want. But of course, this means that we are also not covering parts of the firmware that have to deal, for example, with the scheduler, or and this is actually a problem, because the one bug we couldn't find again was in the scheduler, and we were not really testing that code. But what really makes emulation-based approaches effective is that we can tweak it. We can tweak the emulator in several different ways, making it have some custom checks that it wouldn't have in a normal situation. So we can identify some patterns for bugs. We can, for example, try to follow memcopy calls, trying to to catch the case where we end up reading memory in some addresses that we shouldn't be reading, or we can use symbolic execution when we get stuck and we want to try to break some constraints that a normal fuzzer wouldn't be able to cover. These are all things that become possible once you have an emulator, while in black box setting it's impossible to achieve anything like that. At the same time, at some point everything comes at a cost, so if you have a lot of hooks, your emulator will be slower and slower, and there is always a trade-off between how much you reverse engineer and customize your tools and how much you can actually let your fuzzer run and discover things. But let's now dive into one specific bug that we found using emulation-based fuzzing and how we actually exploited it. This is a bug that appears in a function that parses key parameter objects. We find these objects in quite a few messages in the key master task, and it is an out-of-bounds write of exactly 1 byte that can be set to exactly 1, with some constraints on where this write can happen. So at first, when we found this bug, we thought it would be a kind of minor issue, something that cannot really be exploited, but let me drive you through the code. So on the left side, you can see the assembly view, on the right, the compiled one. And the vulnerable instruction is this store byte instruction, where we are writing 1 byte out of bound. Now, as you can see, the value in R1 will be 1, so we are writing 1 byte to exactly 1. But there is an offset that has to go through some checks. And this offset, let's do these checks together. So we have a standard 32-bit value, which first of all is must. So we only care about the least significant byte. This least significant byte has to be smaller than or equal 4 to bypass this this if condition. And there is also a somewhat more complicated bitwise operation. Let's not go into the details, but trust me here, the value we can have here, the values we can have here are only 0, 2, and 4, which means that we can set this offset to any value, but the least significant byte needs to be 0, 2, or 4, which kind of limits where we can write quite a lot. However, what can we do with this? We can reach the vulnerable code, as I said, in many different ways, because this type and this function is called from many different commands, because many different commands have to decode that field. This gives us different base addresses where we will be able to do this out-of-bound write. And if you remember at the beginning, I said that the memory of Titan M is completely static, which means everything will always be at the same place. So 1 byte can be enough. If you can write that 1 byte at the right place, that can be enough to achieve interesting results. So what we did was, okay, let's try to generate, always using the emulator, all the possible addresses that we can reach with this primitive, and then let's highlight them in our disassembler to see where, if we find anything that seems to be interesting. And it turns out that at some point we can write 1 byte in a structure in memory that we called keymaster SPI data. This is just a name we gave. It's probably not accurate, but the point is that we can write 1 byte in a field that contains the address where incoming requests are stored. So this structure, to give you a bit more context, is holding information about SPI exchanges between Android and the Titan M. So this is the way the two communicate. We have this structure for each one of the tasks. So we have the one for keymaster, the one for identity, the one for AVB, and so on. And the point here is that one field tells the Titan M where it should store an incoming request. So we can make it become from 192C8 to to 101C8. So as you can see, requests will be stored quite far from where they would be supposed to be stored. And that was the moment where we understood we could have some fun. But first, let me take a step back and remind you about the situation that we are facing. So we found the bug with the emulator. So we know that the bug can be there, but we are not entirely sure because we are always dealing with emulated code. And when we try to do the same thing on the real device, all we can have is a client to send our messages, NOS client. We have a return code that comes from the library that we are using. And if the command is successful, we also have a response. But that's it, that's all we have. So we don't have a debugger, we don't have any trace if we cause a crash. So thinking about writing an exploit is basically impossible or extremely challenging. So if you remember at the beginning, I mentioned there was this UART interface that the Titan M was using. So the thing is, we ended up having to solder 2 wires into the motherboard of the Titan M, of the Pixel device. Those 2 wires let us access on the hardware level the UART of the Titan M chip and gave us access to a simple console that is really not that interesting. It allows really basic interaction with the chip, things like asking for the version of the firmware or statistics and stuff like that. But this is the place where logs are printed when the chip is printing something. So if at some point of the firmware the chip wants to do a printf, this is the place where logs will end up being written. So what we did was, okay, now that we have access to this debugging interface, let's just try to, once we have overwritten the address of requests, let's try to send bigger and bigger and bigger messages to see what happens. So now we write in 0x101C8, we write bigger and bigger messages to see what happens. And at some point, we understand that the chip starts crashing. So something must be happening. We noticed this thanks to the UART interface again. So what if we try to put a valid address at the end of our payload at the moment where the chip crashes? And what turns out to happen is that we get some logs in the UART. So this is where the UART comes helpful. When you are debugging your exploit, you can always try to jump to some function that prints some code, and in the UART, if you see that those logs being printed, it means you were able to trigger that specific function. So now that we have our logs, it means that we have code execution in that point. That's quite nice, but now what? First of all, what is going on? Because we were writing junk, and at some point we jumped to some function. So our guess is that we are actually overwriting a return address that was pushed to the stack, and then a function wants to jump back to its caller, and it turns out to go into a function that we decided that we wrote. But from now on, getting a proper attack mounted is far from trivial because the stack is not executable and we don't have space to write our ROP chain directly where we start having code execution. So we need to do what is known as stack pivoting, but this is usually done by decreasing the stack pointer or putting a new value in it. We only have one gadget, however, to do that. This is it. It's a bit complicated, but what I want you to focus on is that we will only be able to jump, to move the stack pointer away from 0x20 bytes from where we actually get to run this gadget. So this is not much, but what can you do? This is the only thing we can do. And so we ended up doing something that was a bit crazy, some may say, but that's the only way we could find our space. So we would call this gadget multiple times, moving away from the point where we started of 0x20 every time. So we go up and up and up. And yes, writing some helper values in another place to be able to run this gadget because of the load instructions that are present in the gadget. So once we manage to move our stack pointer away from the beginning, the second stage, now we are over there with our execution, and the second stage, now we can finally do something interesting with our exploit, now that we have the space to do it. But we are still running in a context that is a bit unknown. If you remember, we were overwriting a function address in a point that we are not really sure which tasks or which context it is running on. So basically, we want to have code execution from a command handler to be able to send some results back to Android. And the thing is that these command handlers are written in RAM. So basically, we can try to overwrite these command handlers that are in RAM, then make the new handler jump to somewhere we control, and that's where we're going to be able to write our code to have the full exploit running, because there we will be running in the context of a command handler. So then we will be able to trigger this with a second command and complete our exploit. All of this needs to happen in the space that you see over there, making sure not to overwrite the gadgets we needed to jump on the stack. So this is a bit of an exercise of return-oriented programming while trying to avoid certain addresses that we wrote before. But at the end of the day, we managed to do it. We managed to overwrite the pointer of one command. Specifically, it's called destroy attestation IDs, but it's not important. You can choose any of them. And from there, we are able to move away from the context, the stack of the command handler, and write our final payload elsewhere in the stack, where we are able to have all the space we need and complete our exploit. So once we are here, it's everything is aligned to complete the exploit. As I said, all we need to do is complete the attack as we want, and the thing that makes most sense when attacking something like the Titan M is trying to exfiltrate memory secrets. So what we do is we jump to memcopy with some arguments that we choose to be able to leak arbitrary memory in the memory of the chip. This time doing it with a 0-day. So we are able to leak the secrets that are kept by the chip and practically achieve some damage, let's say, to the security model of the pixel. So let me give you a concrete example, and that is in the context of Strongbox keys. So Strongbox is the hardware-backed version of Keystore. Basically, it is the highest level of security for Android cryptographic keys. These keys are not stored anywhere in plain text, are stored encrypted in the Android file system, and they can only be used by the Titan M that will decrypt the keys and use them to perform the key operation that is requested. So this is the highest level of security for keys in Android, and can we actually defeat it with the exploit that we have? The answer is yes, of course, otherwise I wouldn't be presenting it. But how? The way we can interact with Strongbox keys and perform crypto operations is with 3 commands. Begin operation, update operation, and finish operation. Now, what can we do with the begin operation? We send our key, and let's say we want to do an encryption. So we send our key and our plain text, we say, okay, please, Titan can you encrypt this text with this key? And Titan will say, of course, I will decrypt the key, put it in a fixed address, and then use it to perform the operation. So maybe you can already see where I'm going. Since the key is decrypted in a fixed address, what we can do is get the key blob, so the encrypted key from the Android file system, forge a begin operation request. So we will tell Titan, can you please use this key to perform this crypto operation? And then, instead of sending update and finish operation to actually perform the crypto operation we requested, we run our exploit to read the memory from the fixed address where the key is placed. So we finally extract the key that is protected by the Titan, defeating the strongest level of security for cryptographic keys. The only conditions to be able to run this attack is to be already root in the phone. So, of course, this can be done on a rooted phone or with some kernel exploit, which, by the way, is perfectly within the security model of the Pixel smartphones. The idea is that you have something like the Titan M to be able to protect from a kernel that is potentially already compromised. So you have to be root somehow, and you have to have access to the key blobs to send it to the Titan M. So either of being, instead of being root, you can always have direct access on the hardware, or you have to be able to bypass file-based encryption. The easiest way is to be in the kernel, basically. Now, this bug has been patched, so it's not present anymore, fortunately, but I want to just spend a minute on one potential mitigation that is present in, that is available, and that would make this attack impossible. This doesn't seem to be really that much used in Strongbox use cases, but I think it's still worth a little discussion, which is the creation of authentication bound keys. So the idea is that you can, when generating a Strongbox key, you can add an extra line to ask the key to only be used under authentication. So whenever the user will want to perform a cryptographic operation with that key, the user will have to go through some authentication, either via biometrics or with an authentication factor. And this will add an extra field in the begin operation request that we cannot forge, we cannot access in any way. So if one key is authentication protected, we cannot leak it using the exploit that I showed earlier. So this is an interesting mitigation that, however, is kind of impacting the usability of that key, because if every time you want to encrypt something, you have to authenticate, it is a bit of a hurdle to the final user. So let's just wrap up with some conclusions. The Titan M was an interesting target for us because despite being despite being so hard to interact with it, it still offers a number of different approaches to try to perform vulnerability research on it. With black box fuzzing, you can try to get the surface bugs, so it's easy to mount a fuzzer and see what you can find. While with emulation-based, there is a little bit more work required, but there you can get more interesting results by having more visibility over the target. The idea is that you can also play with both approaches depending on the time frame that you can allocate for a specific task. And these two approaches are extremely portable. They work for any similar target, which is a little bit of the reason also why we want to share these results. We managed to find an interesting zero-day that gave us a code execution exploit on the chip. It was quite a ride to exploit it, but at the end of the day, we can leak any memory region in the chip's memory, which allows to break some of the security properties of the chip, such as the protection given by Strongbox keys. So this is it. You can find all the resources on our GitHub repository, as well as in a blog post where we went over all the little details of the exploitation, which I realize can be a little bit confusing in a few minutes of presentation. And that's it. Thank you very much, and I'm happy to take any questions.
Sì.